So let's take the number of species that occur uniquely in our old field. So that's 1, 2, 3, 4, 5. Right? The other 5 occur in both. And then the number of species that occur uniquely in the forest. Okay? So that would be 5, 6, 7. So the beta diversity between the old field and the forest would be 7. Let's do the same thing for these two communities. 1, 2, 3, 4. There are 4 species that occur in the forest that don't occur in the wetland. That's 5, 6. 6 species that occur within the forest but not the wetland. And then that gives us 2 species that occur in the wetland but not the forest. So beta of the forest versus the wetland would equal 1, 2, 3, 4, 5, 6, 7. That would equal 8. Okay. Then if we look comparing the old field versus the wetland, well, all 10 of these species occur in the field but not the wetland. So old field versus the wetland. And then these 3 species occur in the wetland but not the field. So that's a total of 13 species that are unique to either the old field or the wetland. There are 7 species that are unique to the old field or the forest, and then there are 8 species unique to the forest and the wetland. We don't count in beta diversity the species that are common between our 2 comparison communities. We're only counting the unique stuff, okay, or what people call the change in. These aren't part of the change, they're held in common. These are the new species I picked up, and these are the new species I picked up. I don't consider the ones that are held in common. Okay? Alpha diversity, as measured by richness, number of species within the community. Then we have beta diversity as measured by richness, in this case, which is the change in species richness, or the number of species that are held unique between the 2 communities. Okay? To me, beta is probably the most difficult one to think about because of the way it's defined, but it's an attempt to get at what changed in terms of diversity by considering 2 communities relative to each other rather than just looking at them individually. And then that brings us to the last one, which is gamma diversity. And gamma diversity as a measure is the overall diversity. So if we're measuring it as richness, the overall diversity here is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The gamma diversity is equal to 14 because that's the total number of species that occur in the park. Does that make sense? We're scaling. There's the individual community types, there's the community types compared to each other, and there's the community types all together. The individual communities have a richness value. The comparison between communities is the species that they hold separately, but added together. And then the last is the overall diversity across the park. That's referred to as the gamma diversity. Okay? Again, we're trying to take scale and diversity and consider them together. Okay? All right, so now we've defined out these different levels of diversity. Let's go ahead and tear into some material. It's going to feel a little bit like evolutionary biology material, but I think I've mentioned before in EBE, ecology and evolution are very similar. We work with the same principles, we just apply them over different scales. Ecology is small spatial, small is spatial scale doesn't match the temporal scale. In ecology, we're talking about small temporal scales. In evolution, we're talking about very long temporal scales. So where they come together is where we're at kind of moderate temporal scales. But the processes that play out over these short temporal scales collectively affect the long temporal scales. So we're basically talking about the same stuff. All right, so what let's do is let's start out kind of this scaling discussion of diversity by talking about temporal diversity. Okay? Right. The number of species on Earth has not been constant since the emergence of life about 3.2 billion years ago. Even though the fossil record is incomplete, particularly for those species that showed up early on because they don't preserve well in the fossil record, we can still see some patterns that are evident in the fossil record. Right, so I hope this shows up okay. I'll post these on Blackboard, but I take it with my phone. I had a textbook that I didn't have this figure. But we're looking at basically 3 periods of time, time before present. We're going back 600 million years, and here would be present day. But they're broken into 3 different eras here. So I think they're eras: Cambrian, Paleozoic. Yeah, so the first chart just looks at the Cambrian period, then the Paleozoic era, and then what they're calling modern day, which is after the Paleozoic. We're talking the Mesozoic and the Cenozoic put together. So here's Cambrian, Paleozoic, and then what they're calling the modern fauna. Okay? All right, so 3 different geological periods, but really we could put them all together if we kind of smushed them together. So the idea is in this plot is that the fauna that show up early Cambrian, these would be a lot of animals, right? The Cambrian explosion in 700 million years ago. And then these animals begin to go through an extinction series, right? Where we go from about 100 families, and then within 400 million years, we're down to a very small number of families from these original Cambrian fauna. Then, if we look at the Paleozoic fauna, the Paleozoic starts around here, so Paleozoic on our chart. Paleozoic is around 570 million years ago. So right here starts the Paleozoic fauna. These fauna are showing up on the planet, right? They reach a peak around 400 million years ago, and then this group of organisms begins to decline on the planet. The modern fauna, that should be around 245, I think. I'm looking at this wrong. Right, so this group of fauna are just the ones that are around here. We look at these, they begin to increase, and then the idea is if we showed up another 100 or 200 million years, this group is probably declining, and we would have another group that started earlier on that begins to come into ascendancy. It's just another way to think about what we've talked about before, right? The amphibians were dominant, and then they got replaced by the reptiles, and the reptiles were dominant, and then they got replaced by the mammals, birds, and pollinating insects, right? The bryophytes were dominant, and then they got replaced by the ferns, and then they got replaced by the gymnosperms, who got replaced by the flowering plants. Okay, this idea of overall as an increase. But if we look within any group of organisms on the planet, if we're talking about ancient flora or fauna, there's this increase and decrease, and then while this is decreasing, there's an increase of somebody else and a decrease, and while this is coming down, there's an increase of other groups of organisms. Okay? Right? That gives us this kind of picture overall. If we just look at number of families, like a family richness measurement here, there is an increase in family richness over time. The number of families on the planet has been increasing, and the number of species on the planet has been increasing as well. That this idea of temporal diversity, what's happening to species diversity over time, as measured by richness, again, we can't count the number of individuals easily that were on the planet any time before today, and I would argue we have a hard time figuring out the number of individuals of a species even today. And my expectation is it changes too. But it's fair to say that the number of species on the planet over these long time scales has been increasing, and the increase looks pretty much like an exponential. Okay? So somewhere in this is this idea of making more species on the planet, right? The processes involved in making more species. And even though we tend to think about this as an evolutionary process, we have talked a little bit about speciation from the ecological side when we talked about niche partitioning, the idea of ecological release leading to sympatric speciation. That's an ecological model to explain what we think of as an evolutionary process, the speciation process. Okay? So, what I want to do is take a little bit of time to develop this idea of speciation out, and at the same time deal with it as ecology as well as evolution. So if we have a new species that's appeared on the planet, this could happen a couple of different ways. So let me do a couple of these models for you. I should probably do that before we get into the ecology. One model is this, that you start out with one species, and through natural selection acting on this species over evolutionary time, you end up with a species that, at least morphologically and probably even genetically, is very different from what it used to be, but this species changed into this one over evolutionary time. The second model is this. Where there's some sort of a speciation event here that leads to the formation of two separate species. This one's a much more gradual process. That one is a quicker process. And then finally, species A and species B could produce a species C by hybridizing to produce that new species. Okay? In any event, if we're talking about species B has just appeared on the planet, or species B has just appeared on the planet, or species C has just appeared on the planet, from an ecological standpoint, our species here is going to be very rare when it first starts. There's no way around it. When you make a new species through this speciation event, the new species that shows up is very rare. The mechanism that produced this new species, we recognize two of these. I'll introduce a third, but from your EBE stuff, either I produce a bunch of individuals through allopatric speciation that are going to be rare, or through sympatric speciation, I produce a number of individuals on the planet, again, very rare. So before we continue on with this kind of rarity and what it means for a species, kind of ecological principles, let's just refresh ourselves on allopatric and sympatric speciation. Again, I know we've done this, but it was a while ago in EBE. So allopatric speciation typically involves taking a large population of individuals here and somehow imposing some sort of a barrier that prevents individuals on this side of the barrier from interbreeding with individuals on that side of the barrier. This barrier basically is what it's doing is it's preventing any migration from occurring between these two subpopulations. I cannot get individuals from here over to there and vice versa. There's no migration that's been allowed. Now, once this barrier is established, this barrier could be the Grand Canyon, it could be the Isthmus of Panama, it could be a new mountain range that sprang up, it could be flooding that occurred that separates two pieces of land that used to be next to each other. Well, now that water in that area is now separating those two pieces of land. What I've got are two populations, or two subpopulations, however you want to think about it, of that original population. Now, as part of this barrier being placed, I have a finite number of individuals on this side, and I have a finite number of individuals on that side. And once I have this finite population size, that by definition, these two populations are smaller than the original population. So what I've done is I've increased the force of evolution that we call genetic drift, that random sampling error during meiosis that allows alleles to move to the next generation. I'm altering allele frequencies in these two populations independent of each other because I've lowered the population size. Another sampling error effect is the